right, welcome to day 7 of this unit. We're putting everything together, and this is called Harmonic Motion. So we've got a person seated on a Ferris wheel. We know the radius, we're told, is 100 feet. So the radius is 100 feet, and it makes one rotation every 30 seconds. So that's how long the period is going to be. So that equals our period is 30 seconds. That's pretty fast. The center of the wheel is at 105. So the center is at 105. Now we've got to try and find all the different variables. So we need A, B, C, D, and E is our period. We know our period is 30 seconds. And there is a relationship between the period and the period constant. So the period is, we're in radians, so 2 pi divided by B. So 2 pi divided by B has to equal 30. So do a little bit of algebra here, and we are going to get that or multiply both sides by B. The B's cancel. We have 2 pi equals 30B. Divide by 30. We get B equals pi over 15 after reducing that. So that's my period constant. That's excellent. We've got that. A represents our amplitude. Amplitude is how far from the center to the top or center to the minimum. Well, that's if we're talking about Ferris wheel, that is our radius. So that is 100. C is the phase shift, and D is how far we've translated this vertically, up or down. So that's where the center is, your sinusoidal axis. So that's 105. And the last thing that was described in the paper is, let's see, assume the person is at the center level headed up when they begin. So at time 0, the cart is here. They're going to go up, come back to the center, down to the minimum, back up. And it's going to just continue like that. So that represents their height of where they are as they go around here. Well, it says that at time 0, they are at the center. So there is no phase shift here. And now we've got to decide what kind of equation do we want to write. Well, in this case, since they're at the center heading up, anytime you have a time for a center location or at the sinusoidal axis, it's best to use the sine equation versus cosine. So my equation is going to be y equals A, which is 100, times the sine, since we're at the center going up, times my period constant, pi over 15, times x minus c. Well, I'm putting minus 0 in here just to show you, but there is no phase shift, plus d, 105. So there is the equation that models the height of the car on this Ferris wheel. And when we're sketching these, it's a good idea to sketch out the full period. So one full period is starting at the middle, going up. I have to go back till I get to the middle, heading up. So there's one full period. And the full period is 30 seconds. And we like to typically put in the 5 critical values. So what time are you at the maximum? What time do you cross the center or sinusoidal axis again? And at what time are you at the minimum? These are evenly divided. So I take my period of 30 and divide it in 4. So 30 divided by 4 gives me 7.5. So every 7.5 seconds is where we're at. So 7.5 plus 7.5 is 15, plus another 7.5 is at 22.5, plus another 7.5 puts me at 30 seconds. So there we've completed the equation. The second part now is what height is the rider at 22 seconds? So what I'm really looking for is the function, the height, at 22 seconds. So I am just going to be putting 22 into my calculator here. And I've already loaded this for us. Oops. There we go. So there's my equation. And if I want to know at 22 seconds, I can just come on down here. And I get kind of tired of scanning. So let's go to change this so that it's at independent variable I'm going to ask. Go back to the table. And I'm going to put in at 22 seconds, tell me the y value. So at 22 seconds, the rider's at 5.55. So let's just put that in, 5.55 feet. We also want to know at 41 seconds, where is the rider? That's an S. So again, I'm going to come back here and put in 41. And the writer is at 179.31. And that we've created our sinusoidal model for our Ferris wheel height, and we've plugged in some different heights to see, or plugged in some different times to see where the writer is at these times. And we can double check this for sanity's sake. At 22 seconds, so that'd be right about here, they're just above the minimum value. Oh, and we didn't put the minimum value here. So the center was at 105. If the radius is 100, the lowest they get is to 5, and the highest is 205. Because the amplitude plus the center gives you the maximum. The center minus the amplitude gives you the minimum value. So that makes sense that 22 seconds, they are almost to the minimum value since they hit the minimum value at 22.5. And now let's move on to the second problem. So our second problem involves Mars rotating around the sun. And it takes 1.8 years. So that equals my period. So we know we're dealing with our time unit is going to be years. And the distance varies from 205 million kilometers to 249 million kilometers. Okay, so our minimum and our maximum there. And after 0.2 years, Mars is at the max, okay, of 249 million kilometers from the sun. So we want to sketch this, and then we're going to have to write an equation and use the equation. So let's fill in what we know. And again, I always start off by creating this little chart. The sinusoidal axis is in the middle. Maximum we know is 249. Minimum is 205. So halfway between these two is our sinusoidal axis. And we can get this one of two ways. We can add these together and divide by 2. I think that's the easiest. When we do that, we get 227. Or what we could have done is subtracted them, divide the difference by 2, which was 44. Or the difference was 44, divided by 2 is 22. So the difference here is 22. That difference represents our amplitude also. So let's see. We know A is 22. B is the period. Okay, we don't quite know that yet. C is the phase shift. D is the sinusoidal axis. That's 227 million kilometers. And E is the period, which is 1.8 years. And we're going to stick with radians just because that's what we typically do. So my period, 1.8 equals 2 pi divided by B. And again, we just need to do a little bit of algebra here. Multiply both sides by B. It cancels here, and then divide by 1.8. So we get B equals 2 pi over 1.8. And normally I would not like that, but I'm just going to be plugging this in the equation, so I'm just going to leave it just like that. 2 pi divided by 1.8. Okay, and the last thing we were told is that at 0.2 years, Mars is at its maximum distance. So it's up here. And we know since it's sinusoidal, it's going to do that kind of pattern. And this time right here is at 0.2. All right, here's where we have a completed period then. Now, we know that the completed period is 1.8 years. However, I didn't start at 0. I started at 0.2. So the time value here is going to be 0.2 plus 1.8. So that is 2.0. And again, I'm just going to put a little note here. That was from 0.2 plus the period of 1.8. So that's how we got the 2. I also want to mark in my time, those 5 critical points. I've got the starting and the ending times, but I need to get these 3 in the middle, when I'm at the center, when I'm at the minimum, and when I'm back at the center. So I take my period of 1.8, and again, I divide it by 4. We always want to divide by 4. Okay, so we divide that by 4. Okay, when we divide that, we get 0.45. So I'm going to take my starting time, or it's not the start, it's the time that I know the location of Mars. So 0.2 plus 0.45 is 0.65. So that's how long it takes to do that quarter period. To do another quarter period, I take 0.65 plus 0.45, and I get 1.1. Add another 0.45 to that, and I get 1.55. And if I were to add another 0.45, I get to 2.0. So at exactly 2 years, it's back at the maximum. Okay, so now I've got all the information. My phase shift, I was told, was 0.2. And that's my phase shift if I'm looking for when it's at the top. And our function that starts at the maximum value is cosine. So I'm going to write a cosine equation for this. So y equals 22, the amplitude, times positive cosine, because I know the time when it's at the maximum, multiplied by my period constant, 2 pi divided by 1.8 times x minus the phase shift. So don't forget that this is a minus here. If you've moved to the right, then it is a minus in the equation, plus d, which is 227. And that is the equation for this problem, or defining Mars. This was part C. This part up here was part A. Part B, we really needed this to find how far Mars is from the sun after 1 year. So I'm going to be putting a 1 in for that equation. So again, I've put my equation to the calculator. I'm going to go to my graph, or to my table, and I want to put in a 1. So I want to see where it is. So it is at 205.24. 205.24 million kilometers away from the sun. Let me just double check that, because that number at 1 year, yeah, I guess that makes sense. At 1 year, it's close to the minimum value. Okay, that's ABC. D was how long is the Mars at least 215 kilometers from the sun? At least 215. So 215, I'm going to go ahead and draw that in. So here's 215, because again, we're talking about the y value. And that's about right here. So how long is it at least that far away? Well, if I know the time that it gets to exactly 215 miles away, it then is going to continue being more than 215 million kilometers away until it gets back to this point. So if I could find these two times and subtract them, that gives me the time, this distance right here is time, of how long it's further away than 215 kilometers. So we're going to use our calculator for this. And when we use the calculator for this, we want to adjust the window to make it work for us. So I'm going to go into my window, and for x minimum and maximum, I'm going to have at least 2 cycles. So I'm going to go from 0 to 4. So that covers at least 2 full cycles. My minimum, I don't want to start at 0 since this starts at 205 million kilometers. So I'm going to put 205, maximum 249. And I want to see the intersection points. So what I'm going to do is go to my y equals, and for y2, I'm going to put in the value that I'm looking for the intersection, 215. And now it sketches it in. So it started at the maximum, it comes down here. This would be at 1.1 years. Up here is at 2.0 years. And what I'm looking for is this intersection and this intersection, because all this time here, it's further away. It's larger than 215 million kilometers. So second trace, I'm looking for intersect. And I just want to get let's get, I'm just looking right here to see where my cursor is. And there, you can see the cursor. That's close enough. And we hit enter 3 times. So the first intersection point was at 1.24. So I'm going to just put x1 equals 1.24 years. And I'm going to do the same thing. Second trace, option 5. But this time I need to move the cursor over to here. Because again, I'm looking for how long is it further away. So go ahead and move that cursor close to the intersection point that you want. That's close enough. And enter 3 times. And I get 2.47. So x2 equals 2.47 years. The difference between these is how long Mars was at least 215 million kilometers away from the sun. So 2.47 minus 1.24. Was that 1. That was 1.38. Excuse me. I already had the answer written down. Equals 1.24. And we can just double check that. Let's just come back over here. I got ahead of myself because I'd already calculated this. Oh, the intersection was at 1.24. Okay, let's pause for a second. Let me redo this. And there we go. Yes, I did make a mistake on just assuming I knew the answer here, but it was 2.47 was the time right here. And time when it was right here at exactly 215 million kilometers away was 1.24 years. The difference between these two is 1.23 years. So again, we were looking for when it was further away from the sun than 215 million kilometers. Sorry about that. Okay, let's go on to number 3. And we're going to look at animals, foxes, and how we can measure their population with the sinusoidal graph. Let's take a look at this one. I'm going to get a clean sheet of paper. All right, so we're looking at our fox problem. Okay, so starting in the year 2003, which we're going to call t equals 0, a maximum of 800 foxes, so 800 foxes, that's our maximum, appeared at t equals 0.9. So this is 0.9 is the time there. So that's going to be our phase shift, we already know. And because we're dealing with a maximum, that's going to be a cosine equation. Okay, the next minimum, so comes down, goes back up. The minimum occurs at 1.5 years. And this was at 200 foxes. Okay, so from this, we've got to deduce everything else. Well, we have to see how long does it take to go from the maximum to the minimum. So 1.5 minus 0.9 gives us 0.6. Note that is not the period. That is from the maximum to the minimum. I now need to go from the minimum back up to the maximum. So it's going to take the same amount of time it took to get to here. So another 0.6 years. So 1.5 plus 0.6 gives me a 2.1. So that's when we're going to hit the maximum. Or we can look at it this way. 0.6 plus 0.6 gives us a period of 1.2. But remember, I need my period constant. And to get the period constant, we take 2 pi divided by the period, 1.2. So 2 pi divided by 1.2. And again, I'm just going to leave it just like that. It's the period constant. The amplitude and my sinusoidal axis now. Again, I'm given a max and a min, so I'm going to just find the center of those two numbers. So 800 plus 200 is 1,000, divided by 2 is 500. And the difference between the center to the max or the center to the minimum is 300. So that's your amplitude. The center is your sinusoidal axis. And because we're dealing with a maximum value, again, that's going to tell me I should use a cosine equation. So y equals the amplitude times cosine times my period constant times x minus my phase shift of 0.9 plus your shift, the sinusoidal axis, how far it shifted up horizontally. And there is my equation. So that's part B. Part C, we need to predict the population at 7, 8, 9, and 10 years. And if we're predicting our population, it really means that if I were to call this population as a function of x, I'm going to put in a 7, an 8, a 9, and a 10. When I do that, oops, I put it off to the side, you can't see it. For 7 and 8, we get the exact same population, 700, and we're going to round that, 760, let's say. At 9 years, we're at 500, and at 10 years, we're at 240. So one thing we could say is that at year 9, we're right at the center. We don't know if we're going up or down in terms of the population, but we are right at the center. And at years 7 and 8, surprisingly enough, we are exactly the same value. So just kind of an interesting thing to happen. So that's perfectly okay. Part D says that foxes are declared endangered when their population is below 300. So we want to know, when is their population below 300? Okay, so here is the graph. I've done more than 2 complete cycles. There is that 0.9. And if I want to, I put in the line representing 300. So that line would be about right here. So if I find this value, we call that x1, and this value, x2, the time between these two values is when the population is below 300. And so I'm going to go ahead and notice it doesn't matter if I chose this is x1 and this is x2, or here x1, x2, or here x1, x2. Because this is periodic, it stays the same. It doesn't matter which segment I'm measuring. So let's go in and measure that. Option 5. And I'm at 2. So let's see. So I'm right here. Let's go ahead and see. So that is 1.34. And let's do the same for the next one. Now, since I've used this as x1, I have to do this one for x2. Oops. And I get 1.66. The difference between these two values, so delta x, the difference between our x values, gives me how long the population was endangered. And so that difference there is 0.32 years. So for about a third of a year, population is not endangered. That's great. I would have hoped it would be longer than that, but that's okay. And show on the graph that that is true. Well, this is approximately 1.34, and that's approximately 1.66. So there is my time period when I'm less than 300 foxes. Okay, let's go ahead. Actually, let me start a new video because this one's getting long to do the last problem.